Thank you very much. I'm super excited to be here to deep dive into Delta Live tables. I'm going to go through really quickly the introduction, since I think a lot of you saw this morning in the keynote. But the basic idea is this. All data starts off dirty. You have to clean it up before you can actually do any of those cool things like AI, machine learning, or business intelligence. But no pipeline is as simple as that bronze, silver, gold that I just showed you. They're always way more complicated in practice. And so the life of a data professional often ends up being something like this. You get an email from your boss. There's some super critical analysis that needs to be done so they can make decisions about how to move the business forward. You, unfortunately, have only a giant directory filled with JSON data, and it's your job to turn that into a beautiful interactive dashboard that drives insights to move the business. So what do? Well, I'm a little bit biased, but I would always start with Spark SQL and with Delta, and I would start writing some SQL queries. And one of the really cool things about Spark SQL is you can just write a SQL query to ingest JSON data, infer its schema, and then another SQL query that will transform that data by cleaning, filtering, augmenting it until it's ready for that consumption, and you're good to go. I've got my dashboard. Victory, right? Well, unfortunately, no good deed goes unpunished. This dashboard is so useful that they want it updated every single day. Or even worse, every single minute. Oh man, now these SQL queries are not going to be enough. So what does it take to take a couple of SQL queries and turn them into a production ETL pipeline? Well, the first thing you're going to notice is you need to make sure that you actually update all of those different tables in the correct order. You need dependency management, something like Airflow or Oozie or Azure Data Factory. You're going to not want to recompute the entire table every time. So you're going to have to build a framework for recomputing only individual partitions or somehow incrementalizing these queries. There's going to be failures. Mistakes are going to, there's going to be cloud failures or other things like that. So you're going to have to build a whole system for retrying and also checkpointing where you are in a computation so you can pick up where you left off. I'm pretty decent at SQL, but I still make mistakes, and so I need quality checks built into my pipeline to make sure that even when my SQL queries are running, they're also producing the correct answers. I'm producing very important data that might have PII and other things in it, so I have to absolutely govern this data. I cannot just make those results available to everyone in my organization. But I also want it to be discoverable by those people in the organization who should be seeing it, and they need to understand what it means. There needs to be a catalog for it. And then finally, even if I get all of this working, then there's going to be some new requirement from the business, and I'm going to have to backfill. I'm going to have to rerun all of this stuff with a new query that adds some extra information to it. And then finally, we have all of the standard software development lifecycle things of version control and deployment. You want to make sure that as I make changes to my pipeline, I know what changes I'm making. I'm getting them code reviewed by other people. And man, that is really complicated. What you're going to see is this tooling is dominating. You are spending all of your time on these tools and none of the time on the thing you actually should be focusing on, which is transforming data to get value from it. And so the kind of key idea of Delta Live tables is to allow you to focus on getting value from data, on those SQL queries that are actually transforming data and handling all of that other stuff kind of in the background. And so that's why we created this system. The idea is you can go from a query to a production pipeline just by adding the word live. So what is a live table, and how should you even think about it? So the right mental model here is, a live table is defined by a SQL query. And when I say a SQL query, I also include data frames there. Data frames are just another language for writing SQL. They're created and automatically kept up to date by the pipeline. The right mental model here is it's going to be the same as writing create or replace table. So you're just putting that answer there. But by putting the word live, you actually get all of these other magical tools. We manage the dependencies, we control the quality, we automate the operations, we make it easy to collaborate and version control with your coworkers, we save you on costs, and we can also even reduce the latency of these pipelines. In addition to live tables, there's one other really important concept that you need to know, which is streaming live tables. Streaming live tables are stateful, which is actually really interesting, and I'm going to talk in a little bit about what that means. But because they're stateful, they guarantee that they're going to read each input row only once. And that's actually really powerful. You can use it to read from a variety of streaming sources, Kafka, Kinesis, Autoloader, anything that's built into the Databricks runtime. And the key reason you want to use streaming is because it can reduce cost and latency by only processing new data. And as you can see, it's also available from this simple SQL syntax. It's just create streaming live table, and you read from a streaming source using SQL. We manage all the checkpoints and other stuff behind the covers. So how do you use it? This is a really quick, like, what does it take to actually create a pipeline? So you write your live tables in notebooks, but you don't actually run them there. You need to run them in the pipeline execution environment. So after you create your notebook and you write some SQL queries with it, you can go over to Databricks workflows under jobs and say create a pipeline. You can pick one or more notebooks. You can actually combine many notebooks together into a single pipeline, and then you click start, and that's it. We read all of those notebooks, we create a cluster, we create and update all those tables, and we publish them to the Metastore. A key detail here is the software development lifecycle is built into the DNA of Delta Live tables. The idea of development and production are kind of like right there in the UI. You want to use development mode when you're writing your code. In development mode, we keep a long-running cluster there so you can iterate very quickly. You have to wait for the cloud to give you resources each time. The other thing is we turn off retries, because in development mode, there's probably mistakes, and you don't want to sit there trying over and over again for your typo. However, when you want to actually run in production, all you do is click that button in the UI, switch it over to production. We will automatically minimize costs by turning clusters off when they're not used, and we will activate our escalating retries, which I'll talk about in a couple of slides, to make sure that pipeline runs no matter what, even when there's issues in the cloud. So what if I have many tables? Because it's never just one table. It's always a pretty complicated DAG of different tables with dependencies. And this is where live dependencies come in. So there's a variety of ways that you can read data from in Delta Live tables. If you're reading a dependency that's outside of the pipeline, you do it just as normal. So you can read from the catalog, you can read from Kafka, you can read from Kinesis, you can read from Cloud Files, all just using the normal Spark APIs or just by saying from table. But live dependencies are special. Those are the ones that are inside of the pipeline, and they're tracked by the system. And all you need to do to define a live dependency is use the live schema. So you can see in this example, I create a table events, and I read it from some external data set that some other team is managing. But then I create a report off of those transform events, and all I have to do is say live.events, and DLT is automatically going to track that dependency, and it will make sure when I'm doing processing that tables are updated in the right order. So it will first update the events table, and then it will update the report table. The other magic trick here is, since we understand the dependencies, we can do automatic parallelism for you. If your pipeline forks out to 5 or 6 different tables, we'll run them in parallel automatically. But we won't run 100 at a time because we don't want to overload the Spark cluster. These are all things that I've seen people struggle with over and over again when you're writing Spark programs by hand. Just leave these concerns up to the framework. Now, you might say, okay, if I can have many tables in a pipeline, how should I think about pipelines? What are the right boundaries here? And the kind of mental model here is, in general, larger pipelines are going to be more efficient. When you have many different things all contending for the resources of the cluster, it's much more likely that you will get good utilization, that no resources will be sitting there idle waiting for the next thing to happen. But there are many cases where you would want to split things, and usually the right place to do this is at kind of natural split points due to your organization. So different teams might have different pipelines. Different data sets with different purposes might have different pipelines. Different data sets with different SLAs might be different pipelines. So that's kind of a good way to think about it. Yeah, and you do not have to have dependencies. You can actually just put them all into a single pipeline if you want them to all run together. A magic trick here of DLT when it comes to thinking about many tables and the size of your pipelines is our advanced autoscaling. And I want to give some advice on how to use advanced autoscaling. So in general, I say, just leave the default for the minimum number of nodes. Let us scale down as small as possible. For the maximum number of nodes, I suggest that you actually pick the largest number that you're willing to pay for. And the reason here is autoscaling is not going to add resources unless they're going to speed things up. So we'll only add resources if things are going to run faster, which means your job will complete quicker, which means we can shut it down. You're basically leveraging the elasticity of the cloud. And by giving yourself headroom, what this means is someday when your data set grows, as it always does, you don't have to worry about missing your SLA. Now, a big problem with developing these pipelines, especially as they start to get complicated, is it's never just one person working on the pipeline. You have an entire team of people that need to develop safely and collaborate on this code. And we've built a bunch of features into DLT to make this easier. But first, let's kind of walk through what some of the problems are. So in order to do continuous integration and continuous deployment, you need to do testing. And DLT handles this basically with this idea of a target, which is where that live schema is actually going to write into the final metastore. It's a pipeline level parameter, so it's like something you actually set in the settings of the pipeline, and it's a reserved keyword. So why do you need to do all of this? Why all of this extra complexity? Well, let's look at what happens if you do this in kind of the naive way. Let's say I have a production job, and this is before DLT, and so I'm just writing create or replace table, and it's going to generate this report. Now, I as a developer want to make some changes to this report. So I'm going to go ahead and use Git or Databricks repos. I'm going to check out this source code, and I'm going to make some changes to it. But since I'm iterating, I'm going to get it wrong. If I run this code and it's hard coding the destination, it's just going to overwrite that table in production and break all of my downstream consumers. There's no isolation here, and that's a huge problem for continuous integration and continuous deployment. So a best practice here is instead you should keep these isolated. I have seen so many people write these crazy Python string munging things in order to do this, but instead we just built this into the DLT framework. So basically you say where it should publish, and in this case when I have my production pipeline, it will publish to the production database. And then when I have my development pipeline, I'll have it published somewhere else. But you'll notice the code doesn't change. Your code is automatically parameterized by the framework. So the struggling developer will make some changes, say, oh man, that's wrong. Let me try again. They will fix it. And once I validate it and I know that all of my answers are correct, only then will I push this to production. And now the right answer will also be there in production. But you might be saying, okay, well that's great, but how did I even know that was producing the wrong answer? It's really hard to reason about what correctness is, especially when your data sets are too big for you to manually inspect them. And so DLT has this really cool feature called expectations. Expectations are tests, but they're tests that run not only in development, they also run in production. And you express these expectations just like you would constraints in a traditional relational database. So on any table, I can say, I have this constraint that there's a valid timestamp. And what does it mean to have a valid timestamp? Well, this is often very organization specific. It doesn't just mean there's a year, month, and a day. At Databricks, I know the company was founded in 2012. So if there's data from 1970, well, it's probably a parsing error. It's not actually valid data, even though it looks like a valid date. And in contrast to a traditional relational database where the only thing you can do is just abort and throw this data away and throw it to the user, that just doesn't work in a big data scenario when there's going to be tons of messy data and it's actually almost expected that some threshold is. So what DLT lets you do is it actually lets you specify the policy for how violations to your expectations should be handled. I can say, I just want to count how many records are bad and record it. So I can look back in time and say, well, we went from 5% to 50%, something's wrong. You can also choose to drop that data, which is like a filter, but so much more powerful. If you just put a filter on your data, you don't know when you're dropping 50% of it. And so when you use expectations to drop that data, we record exactly how many rows are being dropped, so you can kind of look at it and set alerts on that. And then finally, if this is the regulatory table that you're reporting to the SEC or someone else who, the CEO who can never see wrong answers, you absolutely can choose to just abort the pipeline, send a message to the developer, let them fix it. But it's actually more powerful than that because we rewrite the query plan to track lineage. So in addition to showing you that something failed, we can also show you the input row that caused the failure. So you can take it and turn it into a test case and make sure that you'll never have that failure in production again. Now, you might say, if all I can do is these Boolean predicates against a single value, that can't be very powerful. I have really complicated things that I need to expect about my data. But the magic trick here is you have the full power of SQL to express these expectations. You can use aggregations and joins to assert on pretty complicated conditions. So in this example, a question I always get is, I have this table. How do I know if the primary key constraint, if this is actually a unique column? Well, that's very easy. I'll just create another live table. I will group by the primary key, and I will count how many rows there are. And I will throw an error if anyone goes above 1. And the really cool thing about this is now you can actually assert that condition. This is a valid primary key. And you can actually see which row is violating that primary key constraint. Another example here is on joins. So a really common mistake that I see people do is they get their join condition wrong. in some way. And often what that ends up doing is just silently dropping data, which is very difficult to figure out in your pipeline. But with expectations, you can make this a little bit more powerful. Instead of doing a normal inner join, what you're going to do is an outer join. Just a quick relational database reminder. When you do outer joins, you're basically saying, even if there isn't a match, include this row still, and just show the other side is null. And so what you can do is by changing your inner join into an outer join and then asserting that the side that you're looking for isn't null, you can actually track how many cases are failing to match. They still won't show up in your data set, so you're not polluting it. But now you have observability into where your data is bad. If that's 1 or 2, things are probably good. If it's most of your data set, you've got a problem and you need to investigate it. Now, SQL is great. As you can tell, I really like SQL. In fact, that's why all the slides have been SQL so far. But there's a bunch of things that it's actually pretty difficult to do in SQL. So that's why we totally support Python and all of the things you can do in DLT there as well. Using Python is actually quite simple. All you do is write normal Python functions. You already know the API because it's just Spark SQL. So as you can see here, I'm just using spark.table and spark.select. I'm creating data frames. And all these functions have to do is return a data frame. And then you annotate the function with either DLT table or DLT view, and that will turn it into a table. So if you've got a bunch of existing PySpark code, all you need to do is delete the code that has side effects. By a side effect, I mean something like overwriting a table, writing to that directory. You get rid of all of that stuff. You take your existing data frame code and you just say, this should be a table, this should be a table, and it will automatically figure out the dependencies and make sure all of those data frames operate in the right order. In addition to creating tables, of course, the other reason you might want to have a full programming language is to do UDFs. And of course, you can use Spark SQL UDFs. You can define them. You can define them in Python and use them in SQL. You can mix and match languages here. So you can have multiple notebooks where one is in SQL and one is in Python. A pretty common pattern that I will see is people will use Python for all of their advanced streaming stuff and ingestion. And by the time you get to the gold layer and you're just building business reports, those users are much more comfortable with SQL, but it's totally up to you. The other thing is it works with kind of any of the different data frame languages that Spark SQL supports. So you can use kind of the traditional Spark SQL data frames, but if you're a Pandas user, you can also use Pandas on Spark SQL as well, the project formerly known as Koalas. Another really cool thing about Python is you can use libraries, and we support doing pip installation. So you can just %sign pip install any Python library, including your own Python libraries that you've put on DBFS. And this is a great way to kind of modularize your code. If you have shared utility functions that all of the teams across your organization are using, this is a great way to distribute that stuff. One thing to realize here is even though you're defining that Python library inside of a notebook, because of the way we actually execute everything all together in a single Spark context, libraries are going to be global. So if you install a library in one notebook, it's available to all of the different notebooks in your pipeline. And the order of notebooks and dependencies does not matter here. We do a pre-step where we discover all of the libraries, we install them, and then we run your code. And we're also clever. We try to avoid doing that if the libraries haven't changed and stuff like that. Where Python gets really cool is when you start doing metaprogramming. So metaprogramming allows you to dynamically generate pipelines using code. So you could, for example, read from a schema registry and create a table for every different schema that exists. Or another pretty common pattern I've seen is when you have a bunch of business users who don't even know SQL, but they do know Excel, you can give them a spreadsheet that defines all the tables should exist and their different properties. And then you build this meta framework that just reads from that CSV file and generates tables programmatically. And then, once you call create table, we will just automatically, figure out all the dependencies and do that execution for you. A big problem with pipelines is operations. Like, how am I going to know if this is running? How do I know if it's broken? How do I know how long it's taking? How do I know what the quality is? And the pipelines UI is a one-stop shop for figuring out what your kind of operational status is. So I'm going to walk through different parts of the UI here really quickly. You can visualize data flows through tables by looking at our data flow graph. You can discover metadata about each table in the sidebar, including its schema. You can access historical runs. This is another really cool feature, is you can go back in time and see what was happening in the past, what the pipeline used to look like before you made changes to it. And you can actually control the operations, start, stop, change the settings, stuff like that. And finally, you can actually deep dive into what's called the event log at the bottom. Now, what is this event log? It seems like it's just a fire hose of information, and that's because it automatically records all operations that happen in a pipeline. So you have operational statistics, like how long each different hop of the pipeline took. You have the configuration of the cluster and the pipeline that was used any time, so you can go back in time and see, oh, I changed the memory configuration, that caused a problem, or something like that. It has provenance, so it actually captures the schema of every table, as well as the dependencies between tables. You have this lineage information. And finally, we record the explain of each Spark SQL query. So again, you can kind of see how your analyses are changing over time. And finally, we also put the data quality statistics into the event log. So for every update, you can say how many rows were good, how many rows were bad on a per expectation level. You can also see how many rows were dropped and how many rows were allowed to pass through. If there was a failure, you can see the row that caused the failure. All of that is recorded in the event log. And the really cool thing about the event log is it's actually also data. It's just another Delta table created in your account that you can do arbitrary processing with. So I've seen people do some pretty cool things with this. If you have existing tools like Datadog or Grafana that you need to integrate with, well, just create a structured streaming job that reads from the event log, pulls out the metrics you care about, and ships them wherever you want them to go. If you need to get email alerts for certain conditions, create an alert in DB-SQL that queries the table at some periodicity, and then emails you when something is going wrong. And finally, you have the full power of Databricks SQL, so you can create Tableau dashboards or Redash dashboards and visualize what's going on in your pipeline. Failures are going to happen. The cloud, there's spot failures, there's resource provisioning issues, there's transient errors with storage, there's all these kinds of things. And one of the things that DLT does is we try to automate this failure recovery. So we use what we call escalating retries. So we're actually pretty smart about this because we operate at different levels. So when something goes wrong, first of all, everything is transactional. So operations on Delta tables are atomic. We will never leave a single table in a bad state. But if something does go wrong, that whole transaction will roll back so the table is unchanged. And then we will retry just that transaction. So we'll try to rerun just that flow. And then if that fails a couple of times, well, maybe something is actually wrong with the cluster. Maybe it's not a problem with the query. So we'll actually go and cycle the entire cluster in case its certificates are expired or its disk is full, or I've even seen it where you get a bad stick of memory and it's just corrupting every file that it writes out. And then finally, there's one more magic trick, which is, as you need to upgrade to the latest versions of Databricks runtime in order to get security and performance and other upgrades. But that's often a brittle process. Things change in DBR. Your code might have been doing something incorrect. In fact, we had a bunch of users who had problems because their queries were actually wrong, but an old version of Spark allowed them to run. Spark got smarter to say, no, that query is not invalid, but now their pipeline is broken, and that's a big problem. So we have what we call health-mediated releases for DBR, which means when we run your pipeline, if it fails, we'll look back in time. And we'll say, hey, if it succeeded last time, and that was on a different version of DBR, let's try that version of DBR. And if it succeeds there, well, now we have a pretty good signal that it was the upgrade that caused something to go wrong. We will automatically pin your pipeline to the old version, and Databricks support will reach out to help you fix that problem. So really kind of our goal here is we want to carry the pagers for your pipelines. We want to keep them running without waking you up at night. Now, here comes one of my favorite topics, which is streaming. Streaming is pretty awesome because it allows you to dramatically reduce both the latency and the cost. But I want to start by kind of giving a little bit of a primer on what exactly structured streaming is. So structured streaming is the basis for streaming live tables. If you know structured streaming, you know how to use streaming live tables. But the computation model is a little tricky. It's not arbitrary SQL. The model here is your input is an append-only table that's just continually growing. And there's a bunch of different examples of this. Files that are uploaded to cloud storage look a lot like that. Message buses like Kafka, Kinesis, or Event Hub look a lot like that. Delta tables, where you were only appending to them rather than doing update and merge. All of these are great streaming sources. And also transaction logs of traditional databases. The magic trick is rather than wait for all the data to arrive like normal Spark does, structured streaming knows how to produce results on demand with the data that has arrived so far, and then it knows how to update that answer as new data arrives later. This means you get lower latency because you're only processing what's new, and you can also reduce costs, again, because you're only processing what's new. Using streaming live tables is super simple. So here's an example where I read a bunch of files from the cloud. This is a pretty awesome data source because it natively integrates with the underlying cloud storage systems, this cloud files table valued function that we're using. It will actually subscribe to notifications. So even if you have a directory with hundreds of millions of files, we can still ingest it very performantly. And it magically handles inferring the schema and evolving the schema over time. Of course, you can also do the same thing with Kafka. So here's an example of creating a Python function that uses the standard data stream reader API in Spark to create a table that has all of the data from a specific Kafka topic. And you can use any streaming source that is built into DBR with DLT. The other thing you can do is you can read from other Delta tables, either that are in the pipeline or outside of the pipeline. And to do this, all you need to use is the stream function. So instead of just saying select from table, you say select from stream table, and you will get only the changes that have arrived to that table. But there's a little bit of a caveat here, because remember, structured streaming doesn't understand how to handle changes or retractions. It assumes the data is only added to the table. So you cannot stream from a Delta table that you are merging into, or that DLT is merging into, or that someone is doing updates to, because streaming just doesn't know how to handle that. If you have these updates, you should just be using normal live tables. Don't use streaming. But there's some pretty cool patterns here. A pretty common one that I see is using Delta for infinite retention. This is great because it handles both your regulatory requirements around PII, and makes it just much easier to kind of process all of this data. So the idea here is, ingest from these data sources and use a short retention there. If the data only lasts for 7 days or something like that, you don't even need to think about the PII. It's well within your timeline that you can get rid of it. Avoid complex transformations so that there's no mistakes in this code. You want to ingest the raw data into this bronze table. Then you have this table that you can now, it has infinite history. Kafka, Kinesis, they keep a couple of days to a week. This table can have years of data, whatever your kind of business requirements are. You can do GDPR and other compliance tasks directly on this streaming live table. And then you can also make sure that that table never gets messed up by setting pipelines reset allowed equals false. And I'll talk a little bit about what refreshing means in the next slide. But basically this says never delete this data no matter what. This is my only authoritative copy of it. Another kind of key thing is people often hear streaming and they think it's complex and expensive. And that used to be true, but it is no longer true with structured streaming in DLT. You can choose how often you want the stream to update, and so you can balance the trade-off between cost and latency. If you really want to keep things cheap, you can trigger it manually only when it's needed. If you're kind of in the middle, you can set a schedule. Update it once a week, once a day, once an hour, whatever makes sense. If you have super fresh requirements, set it to run continuously. We will always keep that cluster running. We will always keep that answer up to date. And the magic trick here is the code doesn't change as you move up and down this continuum. So if your business requirements change and you all of a sudden go from 1 week is fine to needing it to be really fast, you can just change a pipeline setting, no code changes, and change your latency targets. I want to talk about chaining streaming really quick. So, as I said, it's very powerful to chain different multiple streams together in a single pipeline. This makes sense when the data is very large, when you can never afford to recompute. Also, when you have very low latency targets. But you have this kind of pitfall. These updates will cause the stream to fail. If you do an update to a table, either manually or using something like apply changes into, well, then when the next time you run, the stream's going to say, I don't know how to handle this change. It'll basically fail. So how do you manage that state? So first of all, what do I mean when I talk about state? Streaming is powerful because it remembers exactly what was processed. So let's say I have this very simple query here that's reading A+1, and let's say I change that code. It's not going to go back in time and update that data that was already processed. Only new data that comes in will use the new code. So you can see that's why only those new rows are using the ×2 instead of the +1. Streaming joins are exactly the same way. If I do a join with a static data set stored in Delta, it'll absolutely work. If I go ahead and change this value, but only that new data is going to pick up the new value. So you might say, okay, well, that makes sense. That state is good. But what if I don't want that state? What if I actually want to recompute everything from scratch? Well, DLT has you covered there as well. We have this pretty powerful tool called a full refresh. You can pick either the entire pipeline or individual tables to full refresh. And what a full refresh does is it clears both the streaming state and the data in the table, and then it will kind of reprocess all of its input data from scratch. So we'll kind of take this old version and run it again, and now all of the rows have been updated using this new thing. And doing a full refresh is as simple as clicking a button in a UI. Again, no special code for doing backfills. It's just built into the framework. But you're saying, well, wait a second. If my only choices are full refresh, which reprocesses everything, or not handling updates and things, what about all of these other things? How do I incrementalize them? And so this is going to be a little bit of a repeat from this morning. If you came to the keynotes, but I'll go through it really quickly. Incrementalization is basically the technique where we can update normal live tables, not streaming ones, updating only the parts that change. If you just do a normal create table, it's obviously very naive. It just overwrites all of the data, not very efficient. What we're working on right now with this new feature called Enzyme is basically the ability to update one row and update that, only process the changes that are there. There are 3 really cool techniques that we want to use for this. One technique is appending new data. The appending trick only works when a query is monotonic. A monotonic query is one where we can prove statically by analyzing the query plan that new input will only produce new output and will never retract a row that was already output. This is very efficient. It's just like streaming, but it doesn't work for updates and deletes. Another trick is partition recomputation. So you split the table into individual partitions by some property of the table. It usually means, usually date or something like that is really good. Please do not do it by customer ID. That is always a bad idea. But what we'll do here is we will track which input partitions change, and then we will recompute only the partitions that need to be recomputed based on those changes. So now you can do aggregations and updates, but the input and output have to have the same partitioning, which I said doesn't always work. For example, if you need to do something on customer ID instead of something much more coarse-grained like date. So here comes the final and most powerful trick, which is merging, using 20 years of relational database research on the incremental maintenance of materialized views. The idea here is we're actually going to analyze the query to compute how the output will change based on some given input. We will compute that delta. So rather than overwriting an entire partition, we'll say this row needs to increase by 17. And then we will merge that change into the table. This is super cool because there's tons of different techniques it can handle. Like I said, there's tons of literature on how to do this, but it's pretty expensive to do a merge, and it's pretty complicated to reason about. So how am I supposed to think about all of this? It seems like you have to be a pretty big expert in relational thinking in order to do this. Well, no more, because of Enzyme. So the idea here is we're building on top of the Spark SQL query optimizer, but we're adding in the delta transaction log. And what this allows us to do is reason about how your inputs have changed since the last time you processed. We'll then build a cost function that automatically figures out which of these techniques apply and then executes the correct one. And it will pick the optimal technique at the end. So that sounds too good to be true. So I would like to invite Mukul to the stage, who's actually going to do a live demo of a preview version of Enzyme. Let's have a round of applause for Mukul.
So it's up there.
Oh, did it do it?
Oh,
yeah, you're going to have to look down.
Okay, well, fine. Mic working?
Yeah, you're good.
Okay, cool. Yeah, so I'm Mukul. I'm going to show a quick demo of how Enzyme can speed up processing of incremental materialized views. So the source data we're going to use for this example is a bronze table we've created called taxi raw. It's a streaming live table managed by a different pipeline, and it's fed by a stream of new events. I want to create a summary table, taxi summary, which is a daily aggregated view of this table. We are going to aggregate by date and then just sum a few fields from it, and I can use this to create dashboards. You'll notice that this table is partitioned by date, just like the raw table is, which will allow the partition overwrite technique that Michael just described to kick in. How about change tabs?
I think you should just, control.
There we go. Okay. Cool. So I've got 2 versions of this pipeline. I've got one running with Enzyme and one without. Here's the non-Enzyme one, and I'm going to start updates for both of them. And let's take a look at the settings for both. They're the exact same pipeline. The only difference is that to enable Enzyme, How do I click settings? To enable Enzyme, we've just clicked this checkbox, but they use the exact same notebook that I just showed, and the rest of the settings are the same. And now let's see how they're processing data. Wow, the Enzyme one has already completed. How is this able to finish so fast? Well, while the non-Enzyme version is trying to recompute the entire table, Enzyme is smart enough to know that all of the new records in the source table are today's data, and so it knows that it only needs to update today's record in the summary table. If we look at the data quality metrics, we can see that only one record was written, and that's how the update was able to complete in seconds.
Pretty cool. So thank you so much for joining me today. If you're interested in figuring out how to build your next pipeline with DLT, I put the product page up here. It has tons of user guides and getting started and demos and other things. Thank you so much.